Hi everyone, myself Divya is studying in Shri Venkateshwara College of Engineering. Today in this video, let us discuss about the topic problems that computers cannot solve, the Turing machine from the subject theory of computation. Problems that computers cannot solve, the Turing machine from theory of computation. Introduction to computability. Computability explores that problems cannot be solved using algorithms. Understanding computability helps define the limits of computation. The Turing machine is a foundational concept in this field. What is a Turing machine? A Turing machine is a theoretical model of computation. It consists of a tape, head, and a set of rules for processing symbols. Turing machines can simulate any algorithmic process. The Church-Turing thesis. The Church-Turing thesis proposed that any computable functions can be computed by a Turing machine. It suggests a deep connection between logic computation and algorithms. This thesis is foundational in understanding the limits of what can be computed. The Church-Turing thesis. First is regular, second is TFL, decidable or recursive, or Turing recognizable or recursively enumerable. All this comes under non-decidable. These are the problems which can be solved using the uh, Turing machine. Decidable versus undecidable problems. Decidable problems that have algorithms that provide a solution for all inputs. Undecidable problems lack such algorithms and cannot be fully solved. The distinction is central to the study of computability. The halting problems. The halting problems is a classic example of an undecidable problem. It asks whether a given Turing machine will halt on a specific input. Alan Turing provided that no general algorithm can solve this problem. Does it halt? Halt means no. Yes means it will start a loop forever. Proof of the halting problems. Turing's proof uses a technique known as diagonalization. It constructs a contradiction by assuming a solution exists. They establish a clear boundary between a decidable and decidable problems. Halting problem is undecidable and the proof is given below. Consider a computation of D with input RD. The input to D is representation to any arbitrary Turing machine and the diagram is given below. It examines the preceding computation. We see that D halts input RD if D does not halt input RD, which is a contradiction. Therefore, the original assumption is wrong and the problem is undecidable. Examples of undecidable problems. The halting problem is just one of many undecidable problems. Other examples include post correspondence problem and the word problem. These problems illustrate the limitations of algorithmic computation. Other undecidable problems. It is also impossible to write a program that has the ability to inspect any other programs and determine whether it halts on all inputs, halts on input 0, outputs 2x, on input x, computes f of x is equals to 2x, outputs 1 on input 0. These problems are called undecidable. These are the examples of undecidable problems. Implications of undecidability. Undecidable problems have significant implications for computer science. They highlight the limitations of automated decision-making systems. Understanding these limits is crucial for developing reliable software. Decidability and undecidability. To discuss decidability or undecidability, we need Turing machines, and to discuss Turing machine, we need formal languages and strings and alphabets, and a bit more. Our Turing machines are defined as M is equals to Q summation, row, and transition. Q it is represents the states including start and a stop state, and summation includes input alphabets, and row includes tape symbols and includes B as a blank symbols, and transition it includes transition symbol. Turing machine works on the tape string. When the machine starts, input is written with the alphabet, and then it starts, output is written on the alphabet, and summation must therefore be a subset of gamma. Input can be written on the tape. The role of incompleteness. Gödel's incompleteness theorem relate to the problem in computation. They demonstrate that in any sufficient powerful system, there are true statements that cannot be proven. This concept parallels the undecidability in Turing machines. Simplified Gödel incomplete theorem diagram has been provided here. Complexity classes. Complexity classes categorize problems based on their solvability and resource requirements. P, NP, NP complete, and NP hard are key classes in computational complexity. Some problems are known to be undesirable yet fall into these complexity classes. P and NP, NP complete, NP hard, easy, medium, hard, and hardest. Practical implications of undesirable problems. Undesirable problems influence software development and algorithm design. Developers must often work within the constraints proposed by undesirability. Recognizing undesirable problems can guide better problem solving strategies. Undesirable problems. A decision problem or a language is decidable if there is a Turing machine that solves the problems. Leaves a yes on the tape when the string is acceptable, leaves a no when it is not. A problem or a language is undecidable if there is no Turing machine that solves or decides that problem. The terms solvable or unsolvable are sometimes used instead of decidable and decidable. Real world examples. Certain scheduling problems in operations research are undecidable. Software verification often encounters undecidable scenarios. These examples demonstrate the relevance of theory in practical applications. Objectives or purpose of operational scheduling: maximizing resource utilization, reducing manufacturing time, minimization of inventory, labor efficiency utilization, improving service level, enhancing profit and outcomes. Future research directions. Researchers continue to explore the boundaries of computability. New models of computation, such as quantum computing, raise further questions. The ongoing study of undesirable problems remains a vibrant area of inquiry. Limitations of algorithms. Not all problems can be solved by algorithms, highlighting inherent limitations. This realization has led to the development of heuristic or approximate methods. Understanding limits is essential for realistic expectations in computer science. Limitations of experiments. It is necessary to implement the algorithms, which may be difficult. Results may not be indicative of the running time on the other inputs not included in the experiment. In order to compare two algorithms, the same hardware and software environment must be used. Conclusion on Turing machines. Turing machines provide a foundational understanding of computation. They illustrate the boundaries of what is computable. This framework remains influential in both theory and practical applications. Topics: Turing machines again, formal definition, instantaneous descriptions, moves, transition diagram, language accepted by Turing machines, what is computable. These are the things we have discussed in this video. Historical context. Turing machines were introduced by Alan Turing in 1936. The concept emerged from early expectations in logic and mathematics. Turing's works laid the groundwork for modern computer science. Turing Award. The Turing Award is named in honor of Alan Turing. It recognizes lifelong contribution to the computing community. The award serves as a reminder of the profound impact of Turing's idea. Educational importance. Teaching the concepts of Turing machines is vital in computer science curricula. It encourages critical thinking about algorithmic limitations. Students learn to approach problems with a deeper understanding of computability. Philosophical implications. The limitations of computation raises philosophical questions about intelligence. Can machine ever truly replicate human reasoning? This question challenges our understanding of consciousness and cognitive science. Closing thoughts. The study of computability continues to shape computer science and mathematics. Turing machines remain a crucial concept for understanding these fields. Reflection on what computers cannot solve leads to deeper insight into technology. Thank you for watching this video.